So we operate what's called an eddy covariance system above the mangrove. So we build a tower and we measure the changes in carbon dioxide above the forest. And from those measurements, we can figure out how much carbon the forest is absorbing from the atmosphere. It's the only one of its kind in the world. And with that, we coupled some measurements of changes in tree growth. We look at how much carbon is accreting in the soil, litter fall, and things like that. And then we try to close the carbon budget. So we measure how much is coming out of the atmosphere, measure how much is accumulating on the land surface, and then the difference is how much carbon is actually leaving the system through tidal export. There's a lot of similarities for the mangrove talks that we've seen, actually for all peatlands. There's a lot of similarities in that when you change the forest structure, you inevitably change the amount of peat and the soil carbon dynamics that go on underneath. So I think that they're complementary in that way, and that we see that you can't think of the soil and the forest as sort of distinct systems. They're very much linked. And if you disturb one, you inevitably disturb the other. Well, I think the coastal mangroves are, a lot of them have a tidal component. So they have saltwater intrusion and sort of they're washed over by the tides, or they occur where rivers sort of meet the sea. And the inland freshwater peats are domed systems that are driven primarily by rainwater. So in these rainforests and the high rainfall you get in Indonesia sort of supplies the water inland and helps form the peat. These studies, carbon budgeting stuff in the mangroves, it's been sort of piecemeal here and there. It's very difficult to work. And when you talk about closing a carbon budget, it's an open system that's sort of like, you have freshwater inputs from inland, and you have the ocean coming in, everything's sort of mixing around. So it's sort of hard to quantify carbon budgets with traditional methods. And that was one reason why we used the tracer experiment, because when you have these dendritic tidal channels, you can't really apply a traditional mass balance approach. So with our work and the work that other people have been doing, you're starting putting the pieces together, and you begin to see that the cumulative effect of these mangroves worldwide is disproportionate to the overall cover. So the tracer experiment was a new experiment that we tried, where we labeled some water. We have an inert tracer called sulfur hexafluoride. It's a gas, and we bubble it into the water, and it has a very low detection limit. So we can we can find that gas in the water at something like 10 to the minus 15 moles per liter, which is a very, very small number. But we release it in there at the headwaters of these streams, and then it moves down the river. As it's moving down, it's taking on the characteristics. Its water chemistry is changing based on the influence of the mangroves. So what we did every day, we'd go out and try to find the maximum tracer concentration, and then we took our water samples in the labeled water over several days. And so that allowed us to see the specific influence of the mangroves from the upstream to the downstream areas and the rate of change in the water chemistry as a result. One big thing is how much of the ocean carbon cycle is actually influenced by mangroves. So we're beginning to learn how they affect the atmospheric carbon dioxide concentrations. But what's sort of a big unknown is what the cumulative effect of the mangroves is on the ocean carbon cycle. And because you have so many mangroves in Indonesia and in Australia and this part of the world, it seems like a natural place to study that.